Okay. I'm gonna stop the screen share. So everyone should be focusing on me. Hung-Yu, that might be a great time.
Hey, hello.
Hey, hey.
How are you?
Nice to meet you in person.
Yeah.
Hey everyone, thank you for coming. Hung-Yu, thank you for coming and agreeing to talk to the community. We have a small but very tech-oriented and very enthusiastic community, and we do love to have deep tech talks. And we thought getting one of the writers of a very interesting paper. It was requested of one of the community members. Would be a great way to have some good technical contact. So without further ado, everyone, please accept Hung-Yu, who will from UC Merced, right?
Right.
Who will talk to us about cross-domain fusion classification. Hung-Yu, you're the co-host.
Okay. Yeah.
Take it away. I'll try and monitor the chat for questions. Feel free to either answer as you go or keep them to the end of presentation. It's up to you.
Yeah. Sure.
Cool.
So let me share the screen. Okay. Do you see my screen right now?
Yes.
Yeah. Cool. Okay. Hello everyone. My name is Hung-Yu, and I'm a PhD student from UC Merced. So today I'm going to share our ICLR paper this year, cross-domain future classification via learned feature-wise transformation. And it is a joint work with my colleague 𝗙𝗵𝘂 and my mentor 𝗙𝗲𝘀𝘀𝗶𝗳𝗀 Huang from Virginia Tech, and also my advisor Ming-Shen Yang from UC Merced. So because our problem setting and the solution are built upon the future classification problem, so in the beginning I will talk about the future classification and why do we need future classification. But before that, this is a very brief profile about me. I'm a PhD candidate at UC Merced, which is the 10th newest University of California campus. And my advisor is Professor Ming-Shen Yang. And about my recent research focus, I'm mainly focused on future or meta learning. And also I'm working on some problems related to conditional gain, like image to image translation, for example. So for example, here you can see our IJCV work this year is a unpaired diverse image to image translation framework. I'm also working on problems that related to text to image generation. And previously I was an intern at NVIDIA and Adobe Research, and right now I'm an intern at Google Research. Okay, so why do we need future classification? Well, let's say you want to solve a classification problem right now. Nowadays, you just need to collect a large and diverse data set with ground truth annotation, for example, ImageNet. Then you use these large and diverse data set to train deep neural networks. Then you should expect that your deep neural networks have decent performance. But what about the case you don't have the large data set? For example, let's assume you encounter some new stuff like Cybertruck, which was introduced last year. And you only have a few examples because this is a new stuff. So in this example, we have 3 images that annotated as a Cybertruck. Then you follow the conventional way to train the deep neural networks. And you will find that the deep neural network you train cannot recognize Cybertruck because it overfits to these 3 images. So this essentially is a few-shot classification problem. Generally speaking, the few-shot classification problem wants to learn new task or new classification tasks with only a few examples. Okay, so why do we need few-shot classification? Why is this problem important? Well, if you have few-shot classification models or techniques, you can apply to several fields, such as medical imaging. Imagine due to the confidential issue, you may not be able to collect a larger amount of label data for training your recognition system. And then, for example, robotics. If your robot enter a new environment and start collecting the data, you won't expect you have large amount of label data to reconfigure your robot system. And also, for example, personalized recommendation. Let's say you are using Lightroom or Photoshop to tune your own image. You may have your own preference on the contrast or the coloring. And then this software must adapt to your own preference without the requirement of larger amount of data. And then, of course, the long tail data issue. In most of the data sets nowadays, we must have some categories that only contain few examples compared to the other categories. And that is also a few-shot classification problem. Okay, so that's the few-shot classification problem introduction and why do we need few-shot classification problem. So in the following, I will formally introduce the problem formulation of the few-shot classification problem and also introduce existing solutions. Right now, the major solutions will be optimization-based solutions and metric-based solutions. And because in this paper, we only improve the metric-based solutions, so in this talk, I will only focus on the metric-based method. And then we'll introduce the cross-domain problem setting and why the current metric-based method fails in these problem settings. And also, of course, our own solution. So basically, few-shot classification, as you know, which aims to learn new classification tasks with only a few examples. So in the few-shot classification problem, the model will be given a few examples of novel categories. In these examples, the novel categories are birds, soups, and tanks. And for each categories, we only have three example images for training the system. And we call these labeled examples as the support set in few-shot classification problem. And then given the support set, the goal of the model is to make the predictions on the unlabeled data. For example, here we have an unlabeled bird image. And we call these unlabeled data as the query set. So in summary, few-shot classification problem aims to predict the label or the category of the query set by learning from support set. So to solve this problem, as I said, there are two major solutions right now. The one is the optimization-based method. The most famous one will be MeMo or MetaSGD. And the second major solutions will be based on the metric learning. And in this paper, because we only improve the metric-based method, so here I will just introduce the general form of the metric-based method and some famous work. So here's how metric-based method operates. So given the label support images, the metric-based method first use the feature encoder to map the support images to a metric space. So here, the feature encoder, you can use either AlexNet, VGGNet, or even ResNet, DenseNet. And then after that, if we have an unlabeled image, which is a query image, we also use the feature encoder to extract its metric features on the feature space. Then there's a metric function that make the predictions of the unlabeled image based on the extracted support features and query features. So here you can see the query features is the orange question mark, and it is closer to the blue circle, which is a bird category. So in this case, the metric function will make the prediction that this category is bird because these two features are closer. So formally speaking, we use a feature encoder E to extract support features and also query features. Then the metric function will take the support features, the query features, and also the label of the support features as an input and make the prediction of the category on the query data. So this is the testing phase. And in training phase, we just access the label of the query data and create a cross-entropy classification loss here. And then backward to update the parameters in the feature encoder and also the parameters in the metric function. So this is a general form of the metric-based method. Now all the existing metric-based method follows in this general form, except that they differs in the design of the metric function. So for example, in the very beginning, back to 2016, there's a work called matching networks that use a bidirectional LSTM as the metric function. And then in 2017, this is the most famous one, the prototypical networks. In these networks, they just use a simple Euclidean distance as a metric function. So here, the colored circle are the support features with the class annotation. So the class annotation essentially is the color. So here we have a green class, orange class, and blue class. Then the prototypical networks will extract the center of each class by the average operation. Then now we are given a unlabeled query data, will extract its own features. So let's say the query features are in this position. Then the prototypical networks will simply use a L2 distance or even L1 distance to see the which one is the closest center. So in this example, the class C2 is the closest center. Then the prototypical networks will make the prediction that, okay, so this query data will have the category C2. And then later in 2018, people try to use some parametric model like CNN networks to make to be as the metric function. So in this work, the authors use concate the support and the query features. So the support features was these features, and the query feature was the yellow one. Then after the feature concatenation, and they just throw into the CNN models and then make the relation scores and the final predictions.
Hung-Yu,
Yeah.
there are a couple of questions in the chat. Do you want to take a look or do you want to wait for them?
Oh, sure. Let me take a look. Wait a second. Wait a moment. can I see the chat room right now?
I can read them out to you if you prefer.
Oh. Yeah, I see the chat.
So one by Ofer and one by Amir. Do you see them?
Yeah.
Cool.
The class label will be yeah, so for the class label one, what I mean the class label will be the actual label name, like birds or even Cybertruck in my previous example. The encoder we use hasn't seen our class images during training, right? So yeah, okay, so this is a good question. Basically you can assume that before the training, this feature encoder is not pre-trained by any pre-training process. So the supervision comes from the training stage. You can see if we want this prediction, the prediction of this orange question mark to be birds, then the cross entropy loss here will make the feature encoder to produce the feature diffusion that the orange question mark is closer to the bird, the blue circle one, which is the bird category. So yeah, before the training, you can assume that the feature encoder is not pre-trained by any pre-trained process, but the training of the feature classification method will configure the feature encoder to produce desired feature diffusion.
So I have a follow-up question.
Yeah, sure.
So you said that the model gets as input also the label names, right? Like birds and dogs and so on. So
yeah.
is it like all models use these names? Like, is it fair game to assume that you can, conclude something from the names, or you only need to?
Oh, right. Okay. I understand your question. So no, in feature classification, we do not use the context in the text. So you can assume that this is just bird soup tank. In the training, we just assume this is class 1, class 2, class 3.
Okay.
We do not access the context behind the text information of their label names.
Mm-hmm. So you don't really get the label names, just the index of
Yeah. We just get the class index.
Okay.
Yeah.
Thanks.
Okay. So this is a general form of the metric-based method. Basically, what I'm saying before is that all the existing method differs in the design of the metric function. So here in the 2018, we have a convolution neural networks as metric functions. And then in the same year, there's a paper that uses graph neural networks to as a metric function. So they use the support and query feature to construct a graph, and then they use a graph convolution networks to predict the category of the unlabeled node. And then very recently, back last year, CEPR last year, there's a work that uses a differentiable SVM to make the class prediction of the unlabeled data. Okay, so that's all for the introductions, and then in the following, I'll introduce the cross-domain problem setting in our paper and why this problem is important and our own solution. So the cross-domain feature classification refers to the situation that we use different domain or different data sets during the Fuchsia classification training and testing stage. So for example, here we use the mini ImageNet for training the Fuchsia classification model, but in the testing time we use a CUB, which is a bird dataset for evaluating the model. And why is this problem important? Well, a study last year in ICLR last year points this problem. So the left table shows the case that you train and test the Fuchsia classification model using the same dataset. So if we train and test the model on CUB dataset, you will have the classification accuracy around 70. But in the right table, if you train the model on mini ImageNet, then you test on the CUB dataset, you'll find out that the classification accuracy drops to around 50 or 60. So here's a significant performance drop between the intra-domain case and the inter-domain or cross-domain case. So based on the observation by the ICLR paper last year, we further investigate the potential reason for this issue. We found out that the features diffusion. We found out that the diffusion difference on the metric space causes the generalization issue. So for example, here we have we show an example of the feature space on the mini ImageNet and also the CUB dataset. So you can see that because mini ImageNet is a general or coarse dataset, so the feature or the category sort of span over the whole space. But as you can see during the test time, because we are testing on a birds dataset, so all the features are sort of grouping in a specific subspace. And that diffusion difference between training and testing time causes the generalization issue of the metric function M. So it cannot generalize well from the training diffusion to the testing diffusions. Okay, so that's a problem we found out, and here's our solutions. Basically, we use a feature-wise transformation layers to augment the feature diffusion. So here, this is the original feature encoder, and the red block here is the feature-wise transformation layer we have. And this feature-wise transformation layer will augment the original feature diffusions to be different. For example, grouping in the left side, grouping in the right side, or even grouping in the bottom side. So the goal of this feature-wise transformation layer basically is to diversify the feature diffusion in the metric space, so that the metric function will receive more diverse feature diffusions and improve the generalization ability. So that's the high-level idea of this work. We use a feature-wise transformation layer to diversify the feature diffusions that improve the metric function to generalize better. So specifically, the feature-wise transformation layer we use is as follows. So it's a channel-wise affine transformation operation. So given the input features, with the dimension of C and W and H, we use a channel-wise scaling term gamma and the channel-wise bias term beta to perform the channel-wise affine transformation operations, and then get the augmented image features. But how do we obtain these scaling term gamma and beta? Well, we randomly sample from a Gaussian diffusions parameterized by theta gamma and theta beta. So you can imagine these Gaussian diffusions model the variation of the feature space between different domains. So we grab the scaling term and bias term from two parameterized Gaussian diffusion. So here the problem will be, how do we determine the hyperparameter gamma and theta gamma and theta beta that parameterize the Gaussian diffusion? Well, we can definitely follow the hyperparameter tuning process, which that we collect a validation set and then use the performance on the validation set to select the hyperparameter beta gamma and theta beta. We ask the following questions: can we learn the hyperparameters? So we back to the basic problem. What's the purpose of the hyperparameter theta gamma and theta beta? Well, we train the model on the training domains using the metric-based models and also the feature-wise transformation parameterized by the parameters theta gamma and theta beta. Then we train in that scenario, and the goal is to improve the performance on an unseen domain. So the goal of the hyperparameters theta gamma, theta beta, or shorten the term theta f, the goal of the hyperparameter theta f is to improve the generalization ability of the applied metric model. So we train the hyperparameter theta f by involving these situations in the training stage. Well, the situations will be, we train the model with feature-wise transformation layers on the seen domains and then test it on the unseen domains. But actually, we don't have unseen domains during the training stage. So in our training, we split the seen domains to a pseudo seen and then pseudo unseen domain. Oh, okay. So there's a question in the chat that is the feature-wise transformation applied once the encoder weights are fixed? No, we apply the feature-wise transformation layers and train the feature-wise transformation layers along with the parameters in the encoder jointly during the training stage. Okay, so here's a training algorithms that we optimize the hyperparameter of the feature-wise transformation layers. So in each training iterations, we split the training domains. Let's say we have 5 training domains, then we randomly select 2 training domains, and one will be the pseudo seen domain, and the other will be pseudo unseen domain. Then we first use the pseudo seen domain along with the feature-wise transformation layers to train the models and optimize the parameters in the metric-based model, which is parameterized by theta E and theta M. So in the validation of the pseudo unseen set, we remove the feature-wise transformation layers and then evaluate the performance on the pseudo unseen domain. And these laws, the laws on the pseudo unseen domain indicate the effectiveness of the feature-wise transformation layer. So we use the laws on the pseudo unseen domain to update the parameters in the feature-wise transformation layers. Note that this optimization process needs second-order backpropagation because we need to backprop all the way back to the pseudo seen to the optimization in the 𝗙𝗲𝘀 domain. So any questions about the algorithm? Okay, so that's all for our solutions. We have a feature-wise transformation layer that diversifies the feature diffusion to improve the generalization ability of the metric function. And to learn the hyperparameters in the feature-wise transformation layer, we designed a learning to generalize algorithm to optimize the parameters in feature-wise transformation layers. So in the experiments, we collect 5 data sets, a mini imaginary, CUB, cars, places, and planted data sets. And we apply our solutions to 3 existing metric-based methods: matching networks, relation networks, and graph neural networks. And we apply the feature-wise transformation layers after the batch normalization layers in all the residual blocks of the feature encoder. And the feature encoder we use is the ResNet 10 model. And in the experiment, we have 2 scenarios. The first scenario is that we train on mini imaginary only, and then test on others. Because in this situation, we only have 1 scene domain in the training stage, so we cannot learn the feature-wise transformation layer. In scenario 1, we only show the results of hand-tuned feature-wise, the feature-wise transformation layer that is hand-tuned by the validation set performance. About the scenario 2, we select 1 data set as the testing set, and for example, CUB data set as the testing set, then mini imaginary, cars, places, and planted will be the training domains. And because we have multiple scene domains available during the training stage, we can learn the feature-wise transformation layer. So here is the result of the scenario 1, which is train on mini imaginary and test on other data sets. And in this scenario 1, we only show the result of hand-tuned feature-wise transformation layers. So you can see that overall, by applying the hand-tuned feature-wise transformation layers, we can improve the performance in both the cross-domain case and also, surprisingly, in the intra-domain case. We also compare to some state-of-the-art methods on the scenario 1. So here we compare to the Meta OPTNet, which is a CPR last year that used a differentiable SVM to make the category prediction. And we found out that using the GNN plus hand-tuned feature-wise transformation layer actually performs better than the state-of-the-art methods, which indicates that state-of-the-art method also suffers in the cross-domain problem setting. About the scenario 2, we train on multiple training sets and then test on 1 testing set. So for this column, for example, we'll use the mini imaginary plus cars plus places plus planted as a training set. Yeah, right. So the cars are a bit special. We actually cannot find good performance on the cars dataset because I think it's like the domain discrepancy between cars and the others are pretty large. So our method cannot be effective in this case. Okay, so in the scenario 2, because we have multiple domains available during the training stage, we can learn the feature-wise transformation layer. We denote as the LFT in this table. So you can see that applying hand-tuned feature-wise transformation layer already improved the performance a bit, but after we learn the feature-wise transformation layer, we can further improve the performance on the unseen testing set. So we visualize the performance here. It's a 5-shot classification result. So as you can see, applying hand-tuned feature-wise transformation layer already improved a bit, and then we will have further improvement if we learn the feature-wise transformation layer using our learning to generalize algorithm. We also visualize the feature space. So this is the feature diffusion without applying any feature-wise transformation layer. You can see the difference of the diffusion between different data sets are pretty significant. And after applying the hand-tuned feature-wise transformation layer, you can see that the distance between each diffusion are closer than the original one. Then in the third stage, we learn the feature-wise transformation layer. And because we use the generalization scenario, we involve the generalization scenario in the training stage. So the feature-wise transformation layer kind of model the difference between different diffusions from different data sets. So you can see that after applying the feature-wise transformation layers, the features from different domains kind of mix it up together. And we also visualize the feature-wise transformation layer we learned. So the color indicate the model. So the green one is the matching net, blue one is the relation net, and the yellow one is the GNN net. Then the number here is the residual block in the ResNet 10 models. So this is the first residual block, and this is the last residual blocks. So from this table, we have several observations. The first observation is that for the scaling term gamma, we tend to learn larger scaling term in the shallower layers compared to the deeper layers. And the second observation is that for different models, the feature-wise transformation layer need different magnitude. For example, the relation net, the scaling term learns with the relation net tend to be larger than the scaling term learned in metric networks. So that also shows why do we need to learn the feature-wise transformation layers, because we may need different parameters in different layers, also for different metric-based models. Yeah, so for the conclusions, we derive a feature-wise transformation layer to improve the generalization issue for the metric-based model in the cross-domain feature classification problem setting, and to determine the hyperparameters in the feature-wise transformation layer, we derive a learning to generalize algorithm to optimize these hyperparameters. So you can refer to more details in via this link. We provide the code and also the data that we use in this paper. Yeah, so I think that's all for the talks. Okay, so the question in the chat room that can I provide the intuition that why the right-hand side is better than the left-hand side? So you can imagine, let's say the training domain right now is plenty, which is an orange one. So you train with the orange feature diffusions. The metric function may overfit to the orange diffusions. So during the testing set, it may, if you test the model on different data sets, for example, the cars data set, which is a green one. Then the feature diffusion is significantly different from the diffusion, the metric function C during the training stage. So there's a generalization issue here. And by applying the feature-wise transformation layers, you can see that the orange one and the blue one are sort of mixed together. So in this case, we have the same feature diffusion between the training and the testing set. That will improve the performance of the metric function to predict the category. Is that does that answer your question? Okay, yeah. Okay, so you can find, as I said, you can find the code and dataset and more experiments in this link. So that's all for today. Any questions? Sorry, I cannot hear you.
Anyone else with a question? Did you see somebody asking?
Can you hear me now?
Yeah.
Oh, great. Sorry. So I'll turn off the video also. Hi. So great talk. Thank you. So I have two questions. The first one is you said that you have the loss of the unseen data. So you had there backpropagation that is second order.
Yeah.
So did you have to deal with Hessians, or was it just part of your framework, like PyTorch did it itself?
Oh, so actually PyTorch support the second order backpropagation. So there's no issue except that we need to use larger GPU memory for training our networks.
Oh, okay, great. And the other question was about just a second, the last slide, I think that, it's about the, when you said you would like to diversify the, it's not the last one. I just wanted to ask that when you said that you like to diversify the features, so could you, did you hear of any work that does entropy maximization? Because when I hear the diversification, I think of entropy, and maybe people thought of, let's say, maximizing Jacobians maybe, or something in the way.
Ah, yeah, right. But the problem we solve here is, okay, so let's assume, so I guess what you are referring is the slides here. So let's assume we have cars as the test set. We cannot, in our problem setting, we cannot access the cars data set during the training stage. So we cannot explicitly align the feature diffusion between the training domains and the car data set. So here we are sort of, we are applying a domain generalization strategy. We do not assume the target feature diffusion to be aligned. So as a result, we can only diversify the feature diffusion here to hopefully cover the diffusion during the test set.
I got it. Thanks.
Yeah.
Great. Any more questions from the audience before we wrap this up? Oh, I see Ofer. Maybe ask that live.
Sure, why not? But without a video, I'm sorry. So you said that in order to compute second order derivative, the GPU needs much more memory. Can you elaborate on that?
Oh, well, because you need to keep the, in the second forwarding, you still need to keep the gradient and also the the gradient or in the first forward pass. So I mean, we need to have larger GPU memory. Is that because we during the second forward and back prop, we still need to keep the computation graph of the first forwarding and back propping path.
Sure, sure. And by how much more the memory the GPU needs? Like, roughly speaking, 10 times more, 5 times more.
I think it's like 2 times. 2 times.
Okay. Okay.
Yeah.
Okay. I think there are some methods to overcome this issue, by the way. Like
yeah. So for example, Memo use first order gradient approximation to avoid using the second order. But in this case, we cannot use the first order approximation because we do not have the first order term in this problem, in this method. So yeah.
Okay, thank you.
Anyone else? Looks like we're done. Hung-Yu, thank you very much for coming to speak with us, taking the time, presenting your work. I really enjoyed the talk myself also. Thank you everyone for coming. I see all the things coming up. We have a couple more meetups coming up. We have this Monday about a meetup about distilling Bayesian neural networks with GANs and future learning with StarNet. And we have on July 8th, Wednesday, a meetup dedicated to model distillation, with 2 talks about model distillation. So stay connected, and I'll see you again. Bye, everyone.
Bye. Thank you.